I am Dr. Lakshmi. I am going to handle the subject Linear Algebra and Advanced Calculus for you. In this class, I am going to teach you the basic concepts related to matrices. I hope you are all familiar with the concept, the definition and properties of matrices in your lower classes, right? So let us brush up first what are all you familiar with in your lower classes, and then we move on to the next further concepts, right? So let us first see what is the definition of a matrix, right? Consider these brackets. As you all know, this is the closed brackets. Suppose within these closed brackets, a set of objects, means the objects may be numbers, places, whatever they are. Suppose the set of elements, the set of numbers. For instance, let us suppose that we are considering the set of numbers. Let me take the numbers 1, 2, 3, 4, 5, 6, 7, 8 and 9 I have chosen, right? Suppose this collection of numbers are arranged along the horizontal lines and the vertical lines within the closed brackets. Then we say that the arrangement, what we have shown here, within the brackets, the set of numbers is shown along the horizontal lines and the vertical lines. This arrangement of the given numbers is called as a matrix. So what is a matrix? A system of numbers arranged within brackets along the horizontal lines and vertical lines. Clear? This type of arrangement is called as a matrix, right? Let me give an example with the numbers I have shown here. Suppose we select this 1, 2, 3 along the first horizontal line. Next 4, 5, 6 arranged along the second horizontal line. 7, 8, 9 arranged along the third horizontal line. And no doubt that this arrangement we have already said is called a matrix, right? Now look at the horizontal and the vertical lines, the arrangement we have shown here. We have the 3 horizontal lines, they are called the rows. We have 3 vertical lines, they are called the columns, right? So when the system of numbers are arranged within the brackets along rows and columns, we call it a matrix. As we can see here, there are 3 rows, 1, 2, 3, and also there are 3 columns. We can say that the matrix, whatever is represented here, is of order 3 by 3. While we write it as 3 into 3, but when we read it out, we read it as 3 by 3. And this is called as the order of the matrix, right? And every matrix is always represented with capital alphabets. And whatever the objects arranged within the brackets are known as the elements of the matrix, and they are always denoted with small letters A, B, C and so on. Whereas the matrix itself is represented by the capital letters and so on. So far we have seen what is a matrix, what is its order, how the matrix is represented with capital letters, how the elements of the matrix are represented by the small letters, right? Now let us see how the different types of matrices can be defined. Now let us see what are the various types of matrices we have. Types of matrices, right? In this collection, let us first see what is a square and a rectangular matrix. So the first type we are going to discuss about square and rectangular matrices. Square and rectangular matrices. Let us see what is a square matrix. For example, suppose we have a matrix A. Right? There are 3 rows, also 3 columns. I will place the elements. Suppose we have the elements of the matrix in this way: 1, 2, 3, 4, 5, 6 and 7, 8, 9. We can see there are 3 rows Also there are 3 columns. Therefore we say that the matrix shown here is a square matrix, as there are equal number of rows and columns. Right? So what is a square matrix? A matrix where there are equal number of rows and columns. Similarly, a rectangular matrix means a matrix, let it be capital B, where the number of rows is not equal to the number of columns. We have the different number of rows and columns. For example, we have first row 1, 2, 3, second row 4, 5, 6. How many rows are there? We have only 2 rows. Columns are 3, because the difference is there in the row and column number. We say that this is a rectangular matrix. So what is a square and rectangular matrix? Where there are equal number of rows and columns, it becomes a square matrix. Where there are different number of rows and columns, it is called as a rectangular matrix. Now let us see what is the second matrix. Second type of matrix, row and column matrix. The second type we are seeing is row and column matrix. Suppose a matrix has only one row. Means, suppose the matrix has only one row. Let it be the only row with 3 elements 1, 2, 3. What is the order? Only one row, so it is 1 by. There are 3 columns, it is 1 by 3. So this matrix is having only one row. Whatever may be the number of columns it may have, it has only one row. Therefore, we say that this is a row matrix. Similarly, suppose a matrix has only one column. So, what is the order of this matrix? We have 3 rows and 1 column. So, we may have any number of rows, but if the column number is only 1, we say that it is a column matrix. So, what is a row and column matrix? A matrix having only one row is a row matrix. A matrix having only one column is a column matrix. Now let us see the third type. It is zero and non-zero matrix. What is the matrix type? It is the zero and non-zero matrix. Suppose in a matrix we have all the elements, whatever is the order, whatever is the number of rows and columns. If all the elements in a matrix are 0, we call the matrix as a zero matrix. Right? This can also be called as a null matrix. And coming to non-zero matrix, suppose in a matrix at least one element is non-zero. Whatever may be the row number and column number, if at least one element in a matrix is non-zero number, we call the matrix as a non-zero matrix or a matrix which is not a null matrix. Right? Now moving on to the next type, we have real and complex matrices. We have real and complex matrices. Let us see what is a real matrix first. For example, I am placing the elements here. The first row is 1, minus 1, 0. Second row is 2, 3, 4. So first we should remember this may be a square matrix or a rectangular matrix. For it to become a real matrix, all of its entries must be real numbers. And what are real numbers? It is the set involving integers, whole numbers, natural numbers, rational and irrational numbers. That is called the set of real numbers. And now, if the elements of the matrix are only real numbers, we say that the matrix is a real matrix. And coming to a complex matrix, suppose in a matrix, whatever may be its order, suppose in a matrix, at least one of the element is complex. At least one of the element is complex. For example, if it is 1, minus 1, 3, 2, 4, 5. Clearly, every element is a real number, but every real number is a complex number also, as we all know that. Because the reason is, suppose we consider the real number 2. This can be written as 2 plus I into 0, which is a complex So remember, every real number is complex also. So in the second matrix B, I have shown here, every number is a real number, so the matrix is clearly a real matrix. Moreover, since every real number is a complex number also, we can consider each of the elements as a complex number also. So this matrix can become a real matrix, also a complex matrix, right? For example, if you have in the first row 1, I, 3. I is a complex number. So the matrix become a complex matrix only, it cannot be the real matrix. So what is our observation? Every real matrix is a complex matrix, but the converse is not true. Now moving on to the next type of matrix. Let us see the next type of matrix. We have singular and non-singular matrices. Singular and non-singular matrices. First of all, we must have a square matrix. We consider only square matrices for defining singular and non-singular matrices. Suppose that A is a square matrix and its determinant. You know the calculation? The meaning of determinant of a matrix, right? So if the determinant of the square matrix is 0, then we say that the matrix is singular. Otherwise, what do you mean by otherwise? If the determinant of the square matrix is non-zero, then we say that the matrix is non-singular. As an example, we can consider an identity matrix with 1, 0, 0, 1. Or also we may consider another matrix which is not an identity matrix. For example, if it is 1, 2, 3, 4, when we calculate its determinant, the value is 4 into 1 minus 3 into 2, which is non-zero. Say that the matrix is non-singular. If in case the determinant has become 0, we say that the matrix is singular. Now moving on to the next type, we have identity matrix. This can also be called as unit matrix. So the identity matrix or the unit matrix means a square matrix. First of all, it should be a square matrix wherein all the diagonal elements are 1 and the non-diagonal elements are zeros. So this is called as an identity matrix or a unit matrix. Can also be denoted by I. Because the order is here 3 by 3, can also be denoted by as the principal diagonal of the given square matrix. If other than these principal diagonal elements, all the other elements are zeros. For example, along the principal diagonal we have 2, minus 1, 3. Because the non-diagonal elements are all 0, we say that the matrix is a diagonal matrix. We are not saying anything about the diagonal elements. They may be, one or more of them may be zeros or non-zero. But if other than the diagonal elements, all the elements of the matrix are 0, we say that the matrix is a diagonal matrix. Similarly, the scalar matrix means it is a diagonal matrix. Look at the same example. It can be made a scalar matrix. It is a diagonal matrix first. If in a diagonal matrix, all the elements along the diagonal are equal. So, what is a scalar matrix? A diagonal matrix where all the principal diagonals equal to the same scalar, that is a constant. We say that it is a scalar matrix. Right? Am I clear? So far we have discussed a square and a rectangular matrix. Square means the matrix which has equal number of rows and columns. If not, it becomes a rectangular matrix. Row column having only one row is a row matrix. Having only one column is a column matrix. Remember one thing here. Row and column matrices can also be called as row vector and a column vector. Right? Now the third is 0 and non-zero. If all the elements are zeros, become a zero matrix. Otherwise, non-zero matrix. Similarly, real and complex. If all the elements are real numbers, the matrix is a real matrix. If at least one of the entry is complex, it becomes a complex matrix. Now coming to singular, non-singular. If the determinant is 0, it becomes singular. If the determinant is non-zero, it becomes non-singular. Now coming to identity matrix. If all the principal diagonal elements equal to 1 and remaining all elements equal to 0, we call the matrix as an identity matrix, also called as unit matrix. Now coming to the next diagonal, means non-diagonal elements are 0 in the square matrix, it becomes a diagonal matrix. If in a diagonal matrix, all the diagonal elements equal to the same scalar constant, it becomes a scalar matrix. Right? Now let us continue our discussion on to the next important type of matrices. Let us see what is a symmetric matrix. What is a symmetric matrix? Let me give an example. Suppose we have the matrix A is equal to 1, 2, 2, 4. This matrix is having the order 2 by 2. When I calculate A transpose, right? What is the meaning of getting A transpose? By rewriting the matrix by taking each row as a column. Changing columns to rows and rows to columns. Whatever the matrix we get, it is called the transpose. Also denoted by A power C. Right? Let us find the A transpose of this matrix. First row is 1, 2, so first column 1. Second row 2, 4, so second column 2, 4. Exactly the A transpose and A are equal. So what is our observation here? A transpose is equal to A for the matrix we have chosen. Therefore, the matrix is called as a symmetric matrix. Now, let me tell you another matrix. It is called skew symmetric matrix. So what is the other matrix? Skew symmetric matrix. Suppose in the previous case of defining symmetric matrix, what was our observation? If A transpose is equal to the matrix A itself, the matrix is called as a symmetric matrix. Now in this case of skew symmetric, suppose we have calculated A transpose of given matrix A, but we found that it is equal to minus of A. Then we say that the matrix is skew symmetric. For example, suppose the matrix A is equal to, along the diagonal let us choose 0 elements. It is A minus BC minus A BC. When we calculate A transpose, writing the first row as the first column, it is 0A minus B, second row as the second column, third row as the third column, third row as the third column. B minus is 0, so B minus is 0. When we take minus common, exactly we are going to get the matrix A itself. Therefore, the matrix A shown here is known as a skew symmetric matrix. So when is the matrix skew symmetric? If transpose of the matrix is equal to the negative of the matrix is called as skew symmetric matrix. And when is it symmetric? If the transpose of the matrix equal to itself, it is called a symmetric matrix. Now let us move on to the next type of matrix. Let me write here. It is called orthogonal matrix. It is called orthogonal matrix. Suppose A is a given square matrix. When we calculate its transpose, we found that the transpose is equal to its inverse. The same, in other words, can be written as if A transpose into A is equal to A into A transpose is equal to an identity matrix. We say that the matrix A is an orthogonal matrix. Am I clear? So when is the matrix orthogonal? A square matrix when satisfies A transpose into A equal to A into A transpose equal to I. Remember, it should satisfy both these left and right hand side rules. A transpose into A, also A into A transpose. When each of them is calculated and equal to the same, the identity matrix, we say that the given square matrix is an orthogonal matrix. Let me give an example. Let me give an example. Suppose we have the matrix A equal to 1 by 3 of, along the diagonal we have minus 1, minus 1, minus 1, and the remaining rows with 2's. Let us verify whether this matrix is orthogonal or not. When we calculate A transpose into A, right? Let us calculate first A transpose, means writing each row as a column here. So it is 1 by 3 of first row becoming first column, second row 2 minus 1 2 writing as the second column, third row writing it as the third column. This is our A transpose. Should be multiplied with A. So again we have to rewrite 1 by 3 of the same matrix. Minus 1 2 2 2 minus 1 2 2 2 minus 1. Let us multiply the 2. 1 by 3 into 1 by 3 we have 1 by 9, and let us check what is the product of the two matrices. It is minus 1 into minus 1, 1 plus 2 into 2, 4 plus 2 into 2, 4, we are getting 9. Similarly, when the first row is multiplied with the second column, in order to get the element in this first row second column place, we have minus 1 into 2, minus 2 plus 2 into minus 1, minus 2 plus 2 into 2, we have plus 4. We have got 0. Similarly, when we go on multiplying each row with each column and writing the corresponding elements, no doubt we get 900, 090, 009, which gives us 1 by 9 of 91, 1 by 9 of 00. Matrix as an orthogonal matrix. And remember, these three, the symmetric, skew-symmetric and orthogonal, these are the special types of real matrices. If the same matrices are generalized to the complex case, we have the similar such matrices there also. They are called as correspondingly the symmetric matrix when generalized to complex numbers is called Hermitian. Let us discuss it. Next, the skew-symmetric in the case of complex numbers is known as skew-Hermitian. The orthogonal matrix when generalized to the complex system is known as unitary matrix. Let us also have look at the three different complex matrices. Now let us see what is a Hermitian matrix. What is a Hermitian matrix? Right? Let us see what is a Hermitian matrix. Suppose we have a square matrix A. Maybe real or complex. Because every real number is a complex number, every real matrix is also a complex matrix. So you don't bother about the elements of the given matrix. Suppose that it is a square matrix. If for the given square matrix A, we calculate A power theta. What do we mean by theta? It is A power theta is conjugate transpose. We already know what is the transpose. Right, like writing rows as the columns, and this symbol is called as conjugate bar. This bar represents conjugate. Conjugate means when 1 plus I is a complex number, its conjugate is 1 plus I bar, and it is 1 plus I become minus I. So conjugate of 1 plus I is 1 minus I. Conjugate of I minus I. Conjugate of minus I plus I. So for getting conjugate of a number, we simply change the sign of the imaginary constant I. Right? So what we are going to define the Hermitian matrix? We are calculating A power theta, which is A bar power T, A conjugate transpose. If this is found to be the matrix itself, so what is our definition? if a power theta is equal to A, we say that the matrix is a Hermitian matrix. The matrix is a Hermitian matrix. Let us look at an example. Suppose we have given the matrix A. Let us choose along the diagonal 4, 7 and the remaining two elements 1 plus 3i and 1 minus 3i here. Let us verify whether the matrix is shown here is Hermitian or not. Whether a power theta is equal to A for this matrix is true or not. Suppose we calculate a power theta, which is A conjugate transpose. Right? We are doing transpose by finding the conjugate, or we can write the conjugate along with the transpose, changing row to column. So we choose the first row. Conjugate of 4 is 4. Conjugate of 1 plus 3i. First row should be written along the first column. So the conjugate of 1 plus 3i is written as the element in the second row, first column. Similarly, from the second row, writing the conjugates along the second column, 1 minus 3i become 1 plus 3i, and conjugate of 7, because it is a real number, conjugate is itself, so it is 7. And we can see clearly that this is equal to the given matrix itself. Therefore, our observation is the matrix is here is a Hermitian matrix. Right? So, what is a Hermitian matrix? If the conjugate transpose of a matrix is itself, if a power theta is itself, we say that the matrix is Hermitian. Now, let us see what is a skew Hermitian matrix. What is a skew Hermitian matrix? Suppose A is a matrix and its conjugate transpose is calculated and we found that this is equal to minus A. Then we say that the matrix is skew Hermitian. Very similar to the skew symmetric matrix. Suppose the matrix is given in this way. For example, let us choose A is equal to the elements along the diagonal. Let us choose minus 2i, minus I, and the two other elements let us choose 2 plus I, 2 minus I. Let us see whether the matrix satisfies the rule of this skew Hermitian matrix or not. For that, let us calculate A power theta, which is the conjugate transpose or the transpose conjugate. The first row is written along the column by taking conjugate. So for minus 2i, conjugate is 2i. For 2 plus I, it is 2 minus I. For this second row, we are writing the second column. 2 minus I conjugate is 2 plus I. Minus I conjugate is I. So this is the resulting matrix that we get for a power theta. And now when we take minus common, we have 2i here. So minus of minus 2i. It is minus 2 plus I, right? And this is minus 2 minus I, and this is minus I. So observe compare with the matrix A, we have minus 2i, minus 2 plus I, but this is 2 plus I. So we are not getting minus of A. So clearly we can say that the matrix given here is not a skew Hermitian matrix. Right? Now let me make a small change in the matrix here so that it becomes Hermitian. Suppose here this 2 plus I is taken, this is 2 plus I actually. Suppose we choose minus 2 plus I here. Let us see the changes. Minus 2i, 2 plus I. Okay, first row is the first column, no change in that. Minus 2 plus I become minus 2 minus I, and this minus I become I. When minus is common, we have 2 plus I, and this is minus 2 plus I, we have minus I. Now compare the matrices. It is minus already outside, so we have written minus. Let us now see what is the last type of the complex matrix, which is the generalization of this orthogonal matrix known as unitary matrix. Okay. So let us see what is a unitary matrix. Suppose we calculate the conjugate transpose A power theta and it is found to be A inverse. In other words, this can also be defined as if A power theta into A is equal to A into A power theta, which is equal to an identity matrix of some order, then we say that the matrix is a unitary matrix. Right? You can clearly compare the two, the orthogonal and the unitary. The skew symmetric and the skew Hermitian. Hermitian and the symmetric and Hermitian. So actually these symmetric, skew symmetric and orthogonal matrices, when generalized to the complex case, they are correspondingly known as Hermitian, skew Hermitian and unitary matrices. Right? As an example of this unitary matrix, suppose A is given by 1 by 2 of I root 3 and root 3I. This can be proved to be satisfying A power theta into A equal to A into A power theta equal to I. Therefore, we say that this is a unitary matrix. Thank you.